Vectors. The term vector is used in mathematics and the sciences to indicate a quantity that has both magnitude and direction. When we say magnitude, we are referring to the length of the vector. And of course, direction refers to the direction that the vector is pointed. You will notice that a vector is essentially a line segment, but it's pointed in one direction. So the vector you see here is the vector that starts at point A and ends at point B. And we can name this vector AB with an arrow over the top. Now, usually when we name vectors, we will give them a single letter for a name, such as the letter V. And in the textbook, this letter V will be a bold letter. But when we write bold letters, it's often hard to tell if they are bold. And so when we use single letters to name a vector, we will simply put down the letter, such as the letter V, and we'll put an arrow over the top to indicate that it is a vector. So once again, a vector has magnitude, which is its length, and direction, which is where it is pointed. And vectors can be used to describe things such as the velocity of a moving object, or it can represent force, or displacement, or acceleration. And the magnitude of the vector would be the quantity of what it is you're talking about. So for example, if this vector here represents a car traveling in a particular direction, and let's say the car is moving 50 miles per hour, we would say the magnitude of vector V is equal to 50 miles per hour. And we do have notation for that. Magnitude of a vector can be represented by using absolute value symbols. And so this would represent how fast the car is traveling. And then, of course, the direction, we can use a lot of different ways to describe the direction, such as north, south, east, west, etc., or a bearing or a heading. But a vector has magnitude and direction. Equivalent vectors are vectors that have the same magnitude and the same direction. So think of two cars that are traveling the same speed and also going in the same direction. Those two cars don't have to be in the exact same spot. They just have to be traveling in the same direction and traveling at the same speed. So one of the things that I like to say is that vectors don't have a place. Any vector that has the same length and same direction as another vector is equivalent to that vector. So we would say here, vector V is equal to vector U. We can also add vectors together. Geometrically speaking, when you add two vectors together, you start with one vector, say vector U, and then you place vector V at the tail end of vector U. And when you connect the beginning of U to the end of V, this gives us what we call the sum U plus V. And you can think of this as the triangle law. The other way to understand adding vectors is taking the vector U and V and then making a parallelogram out of those two vectors. So in this case, notice how we draw vector U and vector V coming from the same point. And then when you draw the parallelogram by completing another vector U up here and another vector V here, the diagonal of this parallelogram right here is the sum U plus V or V plus U. So there are two ways to think about the sum of two vectors U plus V in terms of thinking about it geometrically. So for example, if I want to draw the sum of the vectors A and B that you see here, there are two ways I can go about doing this. One way is I can take the vector b here, and I can take that vector and attach it to the end of vector a. So think about taking this vector and moving it over here. So if I draw that vector b the same way that it appears now, but I attach it to the end of a, then the vector that you see right here, that would be the vector a plus b, okay? And you can see a better picture of it down below here. So here we have the vector a. We take the vector b here, we move it over. You can see that right here. And then we simply attach from the beginning of a to the end of b. And that is the vector a plus b. That's one way to do it. The other way to do it, of course, is to take your vector a and your vector b and to create a parallelogram out of those vectors. So in this case, I'm simply going to move vector b to where vector a starts from. So here's vector b. And then I'm going to complete a parallelogram by drawing another vector a here and another vector b over here. And then I simply draw the diagonal of the parallelogram coming from the initial point of both of these vectors, okay? And you can see a better picture of that right down here. In either case, notice that the a plus b you see here is the same as the a plus b that you see here. So there are two ways that you can draw the geometric representation of the sum of two vectors. Scalar multiplication is when we take a constant c and we multiply it to a vector v. And the best way to think about scalar multiplication in terms of its geometric interpretation is if I have a vector v and I multiply that vector by, say, the number 2, basically you get a vector that points in the same direction as v, but it is twice as long. So the magnitude of the vector got multiplied by 2. If I take the vector v and I multiply it by 1/2, I get a vector that points in the same direction as v, but it is now half the length of the original vector v. If I multiply v by a negative number, such as -1, I simply get a vector pointing in the opposite direction of v, so it points this direction, and it has the exact same length. And finally, -1.5 times v is a vector pointing in the opposite direction of v, but it is 1.5 times the length. So a scalar multiple of a vector always gives you a vector pointing in the same or the opposite direction of v. To subtract two vectors, we can think of adding a negative. So if I take the vector u minus the vector v, I can think of that as the vector u plus the opposite of vector v. So if I have two vectors u and v, such as you see here, how do I represent the subtraction of those two vectors? So first, let's point out that negative v would be a vector pointing in the opposite direction of v. So this would be negative v. So if I want to do u minus v, I think of that as u plus the opposite of v. And to do that geometrically, I'm simply going to take the negative v here and attach it to the end of u. So negative v, if I attach it to the end of u, would look something like this. And then u plus negative v would be this vector right here. Okay? And that is the vector u minus v. You can see that right there. So there's a better picture here of what I just talked about. So here I take the vector u, and I take the vector negative v, and I can attach negative v to the end of u, giving me u minus v. Or the parallelogram way of doing it is taking vector u and negative v from the same starting point and then just drawing the diagonal of the parallelogram. But there is a better way to think about the subtraction of two vectors, a much quicker and easier way to do this. And that is what you see right here. So the easiest way to subtract two vectors geometrically is to draw both vectors starting from the same point. So vector u is here, vector v is here. Then we simply connect the ends of those vectors, and u minus v is always going to point toward the first vector. So u minus v would be this vector right here. So as an example, let's draw the vector a minus 2b, given the vectors that we have here. So if I wanted to do a minus b, let's talk about how that would be done. All I would need to do is take the vector a and the vector b and put them down from the same starting point. And then a minus b would just be the connection of the ends of those vectors, and it would point toward a. So that's what that would look like. Now, if I want to do a minus 2b, I'm going to draw the vector a, which is this vector right here. And then I'm going to draw the vector 2 times b. Now, 2 times b is going to be a vector that points in the same direction as b, but is twice as long. So if I draw 2b, it's going to be something like this. And then a minus 2 times b would just be the connection of the ends of those vectors. And remember, it always points toward the first vector in the subtraction. Now, they show you a little bit different way of doing it here. Here is the vector a. Here is the vector negative 2 times b. And then we're simply doing a plus negative 2 times b. But I want you to notice that this vector here is the same as the vector I got here. So you can take either of these approaches to subtracting vectors. You just got to make sure that you pick a method that works for you. Next, we talk about the components of a vector. And this is a way to bring algebra into the vector discussion. In a two-dimensional coordinate system, we can think of a vector as having a starting point at the origin and an ending point at the point a1, a2. In 3 dimensions, we do it the same way. The vector has the starting point at the origin and the ending point at a1, a2, a3. Okay, and that just gives us a 3-dimensional vector. So when a vector has a starting point that is the origin, notice that it is the ending point or the terminal point of the vector that determines what the vector is. So the point a1, a2 and the vector that goes from the origin to the point a1, a2 are very similar indeed. But the vector is the whole directed line segment, whereas the point is simply this point right here. So to tell a difference between a vector and a point, we use the notation that you see here. So we use these pointed parentheses. Same thing in 3 dimensions. When we look at the components of a vector, we are going to put those pointed parentheses around the terminal point of that vector. Next, let's think about vector representations. So the vector that starts at the point 0, 0 and goes to the point 3, 2 in the two-dimensional coordinate system is the vector that we would call 3, 2. However, all of these other vectors are also the vector 3, 2. Every vector that you see in this picture is the vector 3, 2. Because all these vectors have the same length and they all point in the same direction. So in a way, you can think of this vector right here as being sort of the standard form of the vector 3, 2. That is the vector that begins at the origin and ends at the point 3, 2. Whereas all these other vectors, although equivalent, they are not the standard form of that vector. Now suppose that you are given 2 points A and B in the three-dimensional coordinate system. And the coordinates of point A are x1, y1, and z1, and the coordinates of point B are x2, y2, and z2. So basically I have our three-dimensional coordinate system. So here is x, y, and z, the x, y, and z axis. We have some point A, which is the point x1, y1, and z1, and the point B, which is the point x2, y2, z2. And what I want is the vector from point A to point B. So I want the vector AB. And I want that like in standard form. So what that means is I want the equivalent vector such that if it started at the origin, where would it end? To find this vector, we simply subtract the coordinates of the vector, or the components of the vector. And we take the ending point minus the beginning point. So the x-coordinate is x2 minus x1, the y-coordinate is y2 minus y1, and the z-coordinate is z2 minus z1. So in the example that you see here, the vector AB in component form is going to be -2 minus 2, 1 minus -3, and finally 1 minus 4. And if we simplify this, we get -4, +4, -3. Now let's go back and talk about the magnitude of a vector. Remember, the magnitude is simply the length of a vector, and we can denote it using symbols absolute value, or sometimes they'll put double absolute value bars. Depends on the textbook. Basically, to find the magnitude of a vector, you simply use the Pythagorean theorem in 2 dimensions or 3 dimensions. And so the magnitude of a vector A that has an x-coordinate of a1 and a y-coordinate of a2 in the 2-dimensional space is simply the square root of a1 squared plus a2 squared. And in 3-dimensional space, we simply take the sum of the squares of all of the components and then take the square root. We can also add and subtract vectors algebraically. This is a very simple process. So if you are in the 2-dimensional space, with vectors A and B having the components you see here, then the sum of A and B is simply the vector where you add the components of the vector. The difference, A minus B, is where you subtract the components of the vector. And the scalar multiple C of the vector is simply the scalar multiple of each of the components. And the same is true in 3 dimensions. Down below, we have a picture of what vector addition would look like in terms of its components, and also what scalar multiplication would look like. So let's do the following example. Suppose vector A has components 4, 0, 3. Vector B has components -2, 1, 5. First, let's find the magnitude of vector A. And then we'll find the sum of vectors A and B, the difference of vectors A and B, 3 times B, and finally 2 times A plus 5 times B. So to find the magnitude of vector A, we simply take the square root of the sum of the squares of the components of A. So it's 4 squared plus 0 squared plus 3 squared. And this is the square root of 25, which is 5. To find the sum of the vectors A and B, we simply add the components of A and B together. So we are going to do 4 plus -2. That's the first component. Then we'll take 0 plus 1. And finally, 3 plus 5. And this gives us the vector 2, 1, 8. To do vector subtraction, it's pretty much the same thing, except now we are going to be subtracting these components, and you subtract in the order that it was given. So we take the first component of A minus the first component of B. So that would be 4 minus negative 2. And then the second component, 0, minus the second component, which is 1. And finally, 3 minus 5. And if we do the math on this, we get 6, negative 1, negative 2. Next, 3 times B is simply 3 multiplied by the vector B, which is negative 2, 1, 5. And you can think of this as kind of being like a distributive property. So we're going to get 3 times negative 2, 3 times 1, and 3 times 5, which of course gives us negative 6, 3, 15. And finally, 2 times the vector A plus 5 times the vector B is going to be 2 times the vector 4, 0, 3 plus 5 times the vector negative 2, 1, 5. Do the scalar multiplication first. This one is going to be 8, 0, 6 plus negative 10, 5, 25. And finally, we will simply add these components together. So 8 plus negative 10 is negative 2. 0 plus 5 is positive 5. And 6 plus 25 is 31. Most of our work with vectors will occur in 2 dimensions or 3 dimensions. If we think of all the vectors in 2 dimensions, we call this V2, the set of all 2-dimensional vectors. Likewise, V3 is a set of all 3-dimensional vectors. But we can have more dimensions than just 3 dimensions. So in general, Vn is the set of all n-dimensional vectors. An n-dimensional vector is an ordered n-tuple. So it is just a vector that has n components. And we simply list the components of the vector, where all of these numbers are real numbers. Addition and scalar multiplication in Vn are exactly the same as V2 and V3. And we have some basic properties of vectors, and most of these are really obvious properties, so you don't have to think too much about them. The vector A plus B is the same as the vector B plus A. If you add 3 vectors, it doesn't matter if I add these 2 first or if I add these 2 first. When you add a vector to the 0 vector, by the way, the 0 vector is simply a vector where all the components are 0. So if I add the 0 vector to any other vector, I get that vector. If I take a vector and I add to it the opposite of itself, I get the 0 vector. A scalar multiple of A plus B is C times A plus C times B. That's basically just a distributive property. Likewise, a scalar C plus a scalar D multiplied by A is CA plus DA. And finally, if I multiply 2 scalars to a vector, I can multiply the first scalar to the vector and then multiply it by the second. And the number 1 multiplied by the vector A is simply the vector A. Again, most of these properties are very straightforward and obvious. Now let's talk about the standard basis vectors. And these are really important vectors. In 2 dimensions, the standard basis vectors are the vectors that go from the point 0, 0 to the point 1, 0. So that would be the point 1, 0, which we call I. And the other one is the vector going from 0, 0 to 0, 1, which we call the vector j. So in 2 dimensions, I and j are these two vectors. Notice that these are the standard basis vectors because they each have a length of 1 unit, and one goes along the x-axis and one goes along the y-axis, and they are perpendicular to each other. In 3 dimensions, it's the same concept, except now your vectors have to have 3 components. So the vector I is the vector that is 1 unit long and on the x-axis. So it has an x-coordinate of 1 and a y and z coordinate of 0 and 0. So it is the vector 1, 0, 0. J, the standard basis vector along the y-axis, is 0, 1, 0. And finally, k is the standard basis vector on the z-axis, which has components 0, 0, 1. The reason the standard basis vectors are important is because any vector can be written using the standard basis vectors. So think for a minute about the vector A, which has components A1, A2, and A3. You can think of that vector as the vector A1, 0, 0, plus the vector 0, A2, 0, plus the vector 0, 0, A3. Notice that if you were to add these vectors together, the x component, the first component, would be A1 plus 0 plus 0, which is A1. The next one would be 0 plus A2 plus 0, which is A2. And finally, 0 plus 0 plus A3 is A3. Well, the vector here, A1, 0, 0, if you factor out the A1, you can think of it as A1 times 1, 0, 0. Well, 1, 0, 0 is the standard basis vector I. Likewise, we can do the same thing here. If we factor out the A2, we can think of this as A2 times j. And same idea here. This becomes A3 times k. Therefore, any vector in V3 can be expressed in terms of I, j, and k. So for example, the vector 1, negative 2, and 6 is 1 times I, minus 2 times j, and plus 6 times k. So it just gives us another way to write vectors. Now, if I'm being totally honest with you, I prefer this notation over this notation, but this notation has some advantages later on. Similarly, in 2 dimensions, we can always think of a vector A as A1, A2, or A1I plus A2J. So for example, if the vector A is I plus 2j minus 3k, and the vector B is 4i plus 7k, express the vector 2a plus 3b in terms of I, j, and k. Now this may sound really difficult. It truly isn't. 2 ways we can go about doing this. One, I'll just use the notation given. So 2 times the vector A plus 3 times the vector B is simply going to be 2 times the vector A, which is right here. And let's try to remember to always put arrows over our vectors here. And then we have plus 3 times the vector B, which is 4i plus 7k. Because of properties of vectors, I know I can distribute this here and this here. So this becomes 2i plus 4j minus 6k plus 12i plus 21k. And then we just combine like terms. 2i plus 12i is 14i. Positive 4j, and notice there are no j's over there, so that's just going to be positive 4j. And negative 6k and positive 21k is positive 15k. And so this is the vector 2a plus 3b. The other way to do this would be to simply rewrite the vector A as the vector 1, 2, negative 3, and rewrite the vector b as the vector, it's 4i, right? And it's 0j and 7k. And then we can do 2 times a plus 3 times b, the same way that we did it before. And finally, we have unit vectors. A unit vector is a vector whose length is 1. So for example, the vectors I, j, and k that we just talked about, they are all unit vectors because they all have a length of 1. In general, as long as your vector is not the 0 vector, you can find a unit vector that has the same direction by simply taking the vector a and dividing it by its magnitude. So the vector u, which is the unit vector that points in the same direction as a, is simply the vector a divided by its length. So to find the unit vector in the direction of the vector given here, the first thing we would do is find the length of the vector 2i minus j minus 2k. To find that length, we will take the square root of 2 squared plus negative 1 squared plus negative 2 squared, which is the square root of 4 plus 1 plus 4, which is the square root of 9, which is 3. And so the unit vector that points in the same direction as this vector is simply the vector 2i minus j minus 2k divided by 3. And so now all we have to do is divide each one of these by 3. And so this would become 2/3 I minus 1/3 j minus 2/3 k. And that concludes this video lesson.